All right, in this video we're going to talk about higher order derivatives as well as how that impacts our understanding of physics. So we're going to just jump right in here, and this is a pretty easy to understand idea. I'm going to start by looking at a function, f of x, and I'm going to take its derivative by using the power rule. If I were to take the derivative of this thing by using the power rule again, I would end up with 24x. And this thing that I just found is our double derivative. So we have an original function, a first derivative, and a second derivative. And we could just keep on going here. We could continue to take the derivative and find the triple derivative. And then we could take the fourth derivative, the quadruple derivative, and we'd be at 0. And at that point, we would continue and just keep getting zeros. Now, in terms of our world in AP Calculus, things lose meaning after the second derivative. We're going to do a lot with the second derivative. We're not going to really ever get into anything past that. So that is what we're going to talk about. And there's a couple of notation pieces that we should be aware of. So if our original function is f of x, its derivative is f prime of x, and its double derivative is f double prime of x. If our original function is y, our derivative is y prime, and our double derivative is y double prime. If we use our new Leibniz notation, where our derivative is dy over dx, our original function is still just y. Our derivative is dy over dx. Then our double derivative, this is kind of interesting. Our double derivative happens by us taking the derivative of our derivative. And if we examine that, what's happening is that I'm taking d over dx. So remember that this notation or the symbol means take the derivative. So I'm taking the derivative of the derivative, which is dy over dx. Now again, this is where it becomes somewhat handy to think of these, the numerator and the denominator as simply multiplying together. What I'm going to do is take the derivative of y, and the way that we denote that is d squared y. And you can think of it as, again, d times d, which is d squared, times y. And then the denominator would, of course, be dx times dx, or dx squared. So when you see this notation, this is referring to the double derivative using the Leibniz notation. So here's an example. I'm going to go ahead and try to find this, which is the double derivative. So I have an implicitly defined function here, so I'm going to differentiate this using my implicit differentiation skills. And by the way, I can never get to the second derivative until I first have arrived at the first derivative. So first things first, we're going to go ahead and just try to find dy over dx. So we have a product rule scenario, the product of two things. This is a quick reminder on implicit differentiation. So we're going to have the first times the derivative of the second plus the second times the derivative of the first. And this will equal the derivative of the right-hand side, which is going to be 4. And then technically, this is 4 dx over dx. I'm just treating everything with a chain rule here. Although, like I've said in class, these guys really aren't necessary. We can just leave those as 1. So if I clean this up a little bit, and now I simply try to solve for dy over dx. And divide both sides by x. And there we have it. Now, the objective was not to find dy dx, it was to find the double derivative. So I'm going to differentiate this function. And because I've already isolated my my dy over dx, my derivative, this becomes easy, where the derivative, or the double derivative, simply becomes the left-hand side of this function. And now we have a scenario where we've got to apply the quotient rule because I have a fraction. So here we go through low d high, less high d low, draw the line down below, denominator squared must go. Low d high, less high d low, draw the line down below, denominator squared must go, and we simplify. Now you should notice right away that this is a little bit uncomfortable because we have a double derivative defined in terms of the first derivative, which is a little bit weird. But if we remember what this equals from up above here, that the derivative is simply equal to 4 minus y over x, I can substitute this stuff in for dy dx. And it's still a little uncomfortable because I've got a compound fraction, which we want to not be the case, but conveniently we see that this is going to work nicely because these x's are going to cancel out. I'm multiplying x times 4 minus y over x, so the x's cancel, and this will leave me with a negative 4 plus y, a negative negative y. I'm adding. And then some other good stuff happens here. I'm going to have my y and my y cancel out, and I've ended up with negative 4 minus 4, which is negative 8 over x. So the double derivative, final answer, is negative 8 over x. So it just so happens, oh, what a horrible 8. It just so happens that this is an example where the double derivative looks simpler than the single derivative. So you should be scratching your head wondering why we have to ever take the double derivative. At some point, taking the derivative of a derivative of a derivative of a derivative becomes completely arbitrary and meaningless and just lost in abstraction. But there's a super awesome thing that happens at the level of the double derivative, and that is that we are finding the rate of change of the rate of change. So we are literally finding the speed at which the speed is changing. In other words, we're finding the speed of the rate of change of some object or of some item. So in the world of physics, the applications of this are super profound, and this is one reason why physics is so much better understood through the lens of calculus, or maybe not better understood, but it is more easily enabled through the lens of calculus. If you would consider this simple time versus position function with me, let's call this thing x of t. If I were to ask you what's happening at these three separate sections along this graph, you should be able to tell me some stuff about what's happening. You should agree that this is my initial position, and as time ticks by, the position or the distance increases away from where I started. And then if we look at section B here, let's label these. This is section A, this is section B, and this is section C. If I say, what's going on at section B, you should say, well, time ticks on, right? Time is continuing, but the position is not changing. So hopefully you agree that the object, whatever object it is, has stopped moving. And then if I say what's going on for C, you would say that the object is actually going back closer to its starting position, and then it actually goes past it in the other direction. And you should notice something about the slopes of these lines, and you should be comfortable talking about the speed of this particle, if you will. Let's just say this is a particle along these various sections of the graph. You should say that the speed from here to here is constant. It's something like 1 foot per second. The speed along section B is 0. He's not moving. And then the speed along section C, you should agree that because this slope is steeper than the slope at part A, the speed is faster. So he is retreating, this particle is retreating along section C of this graph faster than it made its initial movement forward. So what we're talking about right now is the velocity compared to the position, and this is basic physics. The velocity is a directional speed. So in other words, you're moving 25 miles an hour north. That's velocity, right? You are moving at a certain speed and also in a certain direction. And if we consider again these slopes, we've got a positive slope and then a negative slope. We're talking about the velocity there, and what that is the slope of the position. In other words, I'm just going out of my way here to make a case to say that the derivative of the position is the velocity at any particular moment. If I want to know the velocity at a certain moment in time, I can find the instantaneous rate of change of the position function at that time, and I will know the velocity. In the same way, the acceleration of a particle The acceleration is interested in knowing how the velocity is changing. That's what the acceleration is. When you talk about acceleration, you're talking about the way in which the velocity changes. So if I say that my speed is increasing, this is a super loaded statement. As soon as I talk about speed, I'm talking about a derivative. This is my derivative of my position. And as soon as I talk about something increasing, this is talking about a speed as well. So we're talking about a rate of change. Increasing is a powerful word that causes us to think about a rate of change. And so we're talking about the rate of change of a rate of change. So if we talk about my speed increasing, I'm talking about my acceleration at a certain moment, and that is, as it were, the derivative of the velocity. So back to the graph, if I say, what is the acceleration along this section of my graph? The acceleration on section A is 0. The speed is not changing. The speed is constant. The speed is always up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1. So I know that this is kind of, we're just starting to scratch the surface, but in quick summary of our notation, if x of t is the position, v of t is the velocity, which is the derivative of the position, and the acceleration is the derivative of the velocity, which means that it is the derivative of the position, or in other words, the double derivative of the position. So we have a single derivative, we have an original function, its derivative, and its double derivative, which pretty much completes the picture for our understanding of position, velocity, and acceleration in the context of any kind of movement in physics. Okay, not any kind of movement. But for most of the physics applications that we're going to be looking at, this will be the story that we are reading.